Welcome to IPEN's introductory tutorial on the Dioxin Toolkit. We'll begin today with a brief review of the relationship between the Stockholm Convention and the Dioxin Toolkit. We'll give a bit of the history of the toolkit and its availability. Then we will show you how easily you can find the specific information that you want in the toolkit by taking you step by step through the process of finding its information on identifying sources of dioxins and other unintentional POPs. Parties to the Stockholm Convention are required to prepare inventories of their sources of dioxins and other unintentional POPs, so-called UPOPs. It's obvious that almost all the countries on this map have been colored in blue. These are the 179 countries that have ratified the Stockholm Convention and agreed to meet its obligations. With the exception of some of the wealthier countries, almost all of these countries use the toolkit for preparing their UPOPs inventories. In the Stockholm Convention, Articles 5, 10, and 15, and Annex C largely define the role and scope of the toolkit. Article 5 describes the obligations of parties with respect to the UPOPs. They are required to take steps toward meeting the goal of continuing minimization and, where feasible, ultimate elimination of the UPOPs listed in Annex C. Each party must develop an action plan for meeting this goal. The action plan must include an inventory of UPOP sources and release estimates. The toolkit provides guidance, a template, and technical information for preparing, revising, and updating the UPOPs inventories. Article 15 requires parties to prepare and submit a national report periodically. In these reports, parties describe the steps they have taken to comply with the convention and the effectiveness of those steps. Most parties included their initial baseline UPOPs inventories in their first national report. For each subsequent report, they revise and update their inventories. This webpage is the gateway to all national reports that have been submitted to the Stockholm Secretariat. As you'll note here, national reports are submitted at 4-year intervals. UPOPs inventories provide information that must be included in the national reports, so parties are also revising and updating their inventories at 4-year intervals. Beginning with the second round of national reports, the reports follow a format that includes summaries of the revised and updated inventories rather than the complete inventories themselves. Article 10 of the Convention requires parties to provide the public with all available information on POPs. This means that each party is to make all of its UPOPs inventories, the initial inventory, and subsequent revised and updated inventories available to the public. Annex C lists the UPOPs currently addressed by the Convention. The first two listings are single chemicals, hexachlorobenzene and pentachlorobenzene. The next 3 listings are groups or families of chemicals. The chemicals in each family share the same basic molecular structure. The polychlorinated biphenyls are a family of 209 chemicals. The polychlorinated dibenzoparadioxins and dibenzofurans, also commonly called dioxins and furans, are a family of 210 chemicals. The polychlorinated naphthalines are a family of 75 chemicals. You also may want to notice that chlor or chloro appears in the name of each of the UPOPs currently listed in Annex C. This means that chlorine atoms are an integral part of every molecule of each of these UPOPs. The history of the toolkit begins in 1999. That year, UNEP contracted with 3 people to prepare a preliminary draft of the toolkit. Those 3 people were Hans-Ulrich Hartenstein, a specialist in waste incineration and air pollution control, Patrick Dyke, a fuels and energy engineer, and Dr. Haidelor Fiedler, UNEP's dioxin expert. In 2001, UNEP published a draft of the toolkit and invited feedback from countries that were using it to prepare their inventories. Following modest revision, UNEP published Edition 1 in 2003 and invited comments from both countries and non-governmental organizations. In 2005, UNEP published a slightly revised Edition 2.1, again inviting comments from countries and NGOs. In 2006, at the Stockholm Convention's second Conference of Parties, Dr. Fiedler introduced a proposal that the Conference of Parties endorse the toolkit. However, many national delegations, as well as IPEN and Greenpeace, contended that the toolkit had significant flaws and limitations. In response, the Conference of Parties tabled Dr. Fiedler's proposal and established an expert group to revise the toolkit. The expert group had its first meeting that same year. Beginning in 2006 and continuing until early 2013, the expert group worked to revise and restructure the toolkit. Many new sources were added, especially in the production and use of chemicals and consumer products, and the default emission factors for many sources were revised. For example, emission factors for forest fires and open burning of waste were significantly reduced. To give some notion of the magnitude of the expert group's work, the 2013 toolkit is almost double the length of the 2005 edition and is supported by 3 times as many references. In 2013, the 6th Conference of Parties endorsed the new toolkit and recommended that parties use it to develop their source inventories and release estimates as required by Article 5 and to meet the reporting requirements of Article 15. The toolkit is available in an interactive electronic format, both online and on CD-ROM. In this format, the structure of the toolkit is similar to that of a building with several floors. General information is found in the first level, and each subsequent level has increasingly detailed technical information. The toolkit is very user-friendly. It has internal and external hyperlinks, as well as a full search function. In other words, the toolkit is designed for quick and easy access to the specific information each user wants to find. The toolkit is also available in PDF format so that it can be downloaded and printed. Excel workbooks for calculating release estimates can be downloaded as well. Before we begin exploring the toolkit, I want to remind you of a few important points. Dioxins are indicators for all the other UPOPs currently listed in Annex C. This means that sources that release dioxins will also release the other UPOPs. It means that measures taken to minimize or eliminate dioxin releases will minimize or eliminate the releases of the other UPOPs. And likewise, action plans that are developed to minimize or eliminate dioxins will do the same for the other UPOPs. This is the toolkit's main web page, and it appears here just as it will appear on your computer screen, whether you're using the online version or the CD-ROM. Notice that the toolkit has three main parts. Part 1, General Guidance. Part 2, Default Emission Factors. Part 3, Annexes and Example Inventories. Part 1 offers general guidance for inventory development. That should include identifying sources. So let's go more deeply into Part 1. This brings us to Chapter 1, Introduction and Overview. We've already had a brief discussion of the first major topic, chemicals listed in Annex C, and we've also discussed the purpose of the toolkit. It seems most likely that looking further into the structure and use of the toolkit will bring us closer to the guidance on identifying sources. So let's expand this. This subchapter is an excellent starting point for finding your way around in the toolkit. There are the 4 chapters of Part 1, the 10 source groups of Part 2, and the 53 annexes in Part 3. Clicking on any of these titles will take you to that topic. In Part 1, you may have already noticed that our destination is Chapter 2, Identification of Sources and Estimation of Releases. Let's go into this chapter. So here in Chapter 2, Identifying Sources and Estimating Releases, here I think we've reached our topic for today, identifying sources. We'll begin with looking at the toolkit's offerings as far as sources listed in the toolkit. Reading this portion quickly, you can see that the source categories listed in the toolkit are divided into 10 source groups, and those are presented in Table 1.2.1. Every source listed in the toolkit can be found in one of the 10 source groups shown in this table. However, the table is large and the font is small, so we will look at some of these groups individually. Group 1 includes 7 categories of waste incinerators, each of which is defined by the type of waste that is burned. Group 2, metal production, has 12 categories, most of which involve the production of primary and secondary metals, and the remainder are related, such as production of coke, metal shredders, and thermal wire reclamation. Now note, please, that thermal wire reclamation also includes open burning of circuit boards and cables. Group 3, heat and power production, has 5 categories, each of which is defined by the type of fuel used, and in some cases, the type of stove. Group 4, production of mineral products, has 7 categories, each of which is defined by its product. Group 5, transport, has 4 categories that are defined by the type of engine and the fuel. Open burning processes in Group 6 include two categories of sources: biomass burning, which is the burning in fields of agricultural residue. One class is agricultural residues said to be impacted because they have been treated with chlorinated pesticides that contain dioxins or act as precursors or catalysts for dioxin formation, and/or are burned under poor burning conditions. And the other is non-impacted agricultural residues. The other three sources in biomass burning are sugarcane burning, forest fires, grassland and savanna fires. The second category is open burning of waste and accidental fires, which has 5 sources: fires at waste dumps, accidental fires in houses and factories, open burning of domestic waste, accidental fires in vehicles, and open burning of wood debris from construction or demolition. Group 7, Chemicals and Consumer Goods, is in some ways more complex than most other groups due to the nature of some of its sources. It includes 8 source categories. Some are defined according to their products. For example, pulp and paper production, petroleum processing, textile production, and leather refining. Others are defined according to chemical classes. The source category, chlorinated inorganic chemicals, includes only one source: the chloralkali process that produces elemental chlorine with sodium hydroxide as a coproduct. Chlorinated aliphatic chemicals also has only one listing. It is the production chain for polyvinyl chloride, which begins with the production of ethylene dichloride that is reacted to form vinyl chloride monomer that is then polymerized to produce polyvinyl chloride. The category chlorinated aromatic chemicals lists 14 single chemicals and 2 groups: the polychlorinated biphenyls and 2,4-dichlorophenoxyacetic acid and its many derivatives. Other chlorinated and non-chlorinated chemicals, this category also has only one listing: production of titanium tetrachloride and titanium dioxide. Source Group 8, miscellaneous, includes 5 source categories, while drying of biomass and smokehouses are defined by their fuels. This is not the case for crematoria, and of course, tobacco itself can be considered as a fuel. Group 9, disposal, includes 5 source categories. The first 4 categories are classified according to the type of waste or wastewater received, treated, or released. For non-thermal waste oil treatment, a waste oil is any petroleum-based, synthetic, or plant or animal-based oil that has been used. Many of the 13 source categories in Group 10, hotspots, are related to one or more of the source categories in the other source groups. However, some hotspots are associated with sources that are mentioned but not listed in the toolkit, as well as with unlisted sources that have been identified elsewhere. Also, this group includes one unique source category: kaolin or ball clay sites, where dioxins are thought to have been formed by natural processes, possibly millions of years ago. Now we go back to the complete table 1.2.1 to wrap up this discussion of the sources listed in the toolkit. Remember, from this table you can access each of the 68 source categories listed in the toolkit, the classes within each source category, and the default emission factors for each class. Next, we return to Chapter 2 to learn about sources not listed in the toolkit. Guidance on identifying unlisted sources is presented for the first time in the 2013 toolkit. It is based on this indisputable fact. Dioxin formation occurs only when chlorine is present. This means that a process or activity that involves no chlorine cannot be a dioxin source. However, if even a trace of chlorine in any form, elemental, organic, or inorganic, is present, the process or activity is a potential source that requires further evaluation. More information on identifying unlisted sources is given in Annex 2. Identifying dioxin sources by first finding and following chlorine is not new. For example, both Denmark and the German state of North Rhine-Westphalia screened their chemical production processes to identify those that involve chlorine, and then proceeded to evaluate those that did involve chlorine. The European Union used the same approach with thermal processes. And, as you might expect, this same approach has proven to be very useful in identifying hotspots. In Figure 3.2.1, you see the guidance as a flowchart. While I'm responsible for this flowchart, I have since prepared a simpler and more colorful version that we will look at in the next slide and discuss a bit. Again, chlorine is the key to identifying sources of dioxins and the other UPOPs currently listed in the Convention and addressed in the toolkit. Is chlorine in any form, elemental, organic, or inorganic, produced, used, or present in the process or activity? If the answer is no, there's no need to go further. If the answer is yes, the process or activity is a potential source that requires further evaluation. The evaluation begins with exploring existing resources. For example, look through Annex 2 of the toolkit, through other inventories, through national chemicals lists, pollution release and transfer registers, toxics release inventories, scientific journals and reports. Is the process or activity of interest identified in any of these, or is a similar process or activity identified? If nothing is found that's useful, then it's necessary to screen for dioxins in air emissions, wastewater, products, residues, and or potentially impacted soil, water, and biota, the organisms that live in and on the soil and water. As an example of how sources and hotspots can be identified by screening biota, we invite you to look through the IPEN egg report. For this study, eggs were collected at 20 sites in 17 countries and assayed for dioxins and other UPOPs. The sites were near both known and suspected sources of dioxins. As you see in this summary, 70% of the samples exceeded the European Union's limit for dioxins. Now we'll return to Annex 2. The commercial chemicals and pesticides in these first two tables have been associated with dioxins. Dioxins have been detected in the substances themselves or in gaseous, liquid, or solid residues from their manufacture. There are many other chemicals and pesticides that are known, suspected, or highly probable dioxin sources. Some are still produced and used today. Discovery of dioxins in these chemicals and pesticides and or in their production wastes calls for more thorough evaluation. For example, if the dioxins are in the chemicals and pesticides themselves, where and in what quantities are they used? Are their production facilities monitored? How are the gaseous, liquid, and solid production wastes managed? If dioxins are found in one or more of the wastes from manufacturing a product, the product itself, as well as the accompanying wastes, require thorough assessment, and management of such wastes must be evaluated. Table 3.2.1 lists commercial chemicals associated with dioxins. You see here a number of common, well-known chemicals that are in widespread use. Each one has been included in this table because dioxins have been detected in the chemical itself and or in the air emissions, wastewater, or residues of the chemical manufacturing process. Just taking a few as examples, hydrogen chloride is a secondary product of about 40 manufacturing processes, including, for example, PVC production, and it is used very widely in industrial processes. Trichloroethylene, another secondary product of PVC production, also has widespread industrial uses. Epichlorohydrin is used in the manufacture of epoxy resins, synthetic glycerin, and elastomers. Chloroprene is the monomer of polychloroprene, also known as neoprene, which is used in many consumer products. Now let's scroll down and look at the remainder of the table. Here are some more commonly known chemicals that are in widespread use. For example, PVC plastic, polyurethane. Sodium trochlosine is not quite so well known, but it's used in water purification, as a disinfectant, a biocide, an industrial deodorant, and a detergent. Now let's open Table 3.2.2, currently used pesticides associated with dioxin formation and release. Dioxins have been detected in the 17 pesticides listed in this table. Some are quite well known. For example, in this corrected version showing the contents of the herbicide tiller, you can see that it contains a derivative of 2,4-D, 2,4-dichlorophenoxyacetic acid. 2,4-D is one of the world's most commonly used pesticides, and it's also listed now in the 2013 Toolkit. Again, it's important to remember that when dioxins or other UPOPs are found in a pesticide or a pesticide formulation, the facilities that produce that pesticide and those that prepare its formulations are possible future or current hotspots. Now, let's collapse this table of pesticides and expand the table of additional processes and activities associated with dioxins. Jewelry factories and workshops are quite common, especially in developing countries. A study of 5 small incinerators used to recover precious metals from jewelry wastes found significant dioxin levels in the incinerator air emissions. Clearly, such incinerators are dioxin sources that are comparable to those in source group 1, since it reasonably can be assumed that dioxins also occur in their ashes and other residues. Given these findings for incinerators dedicated to jewelry waste, open burning of jewelry waste and other low-tech recovery methods may have even higher dioxin releases to air and residues and may be comparable to thermal wire reclamation in source group 2. Dioxins have also been found in processed food salt, bamboo salt, and parched salt. The dioxin levels varied according to the fuel used for baking the salt. In short, certain salt processing facilities are dioxin sources comparable at least to household heating and cooking with biomass in Source Category 3. Thank you for your time and attention. We hope that you feel more comfortable with the toolkit now and have a better understanding of how it is used in identifying sources of dioxins and other unintentional POPs.